Hi, everyone. So as you know that just we have completed this ICPC regional Gwalior-Pune regional contest on 18th August of this month. So we also know that total 524 teams we actually accept those requests for this competition. And those are from 166 different institutions. So, and we also witness a very competitive this contest. And this dynamic change in ranking in minute to minute we observe. And the contestant, this contest creates a lot of enthusiasm and patience among the contestant and the judging team also. And my sincere thanks to all contestant coaches, ICPC Foundation, and the global sponsor. Their global sponsor will sponsor for the upcoming, this is our world final at Moscow from 1 to 6 October. And this is Huawei, JetBrain, AWS Educates, and IBM Quantum. And I am also thankful for all the administrations from this is IIIT Pune, then ABB, IIITM Gwalior, and Asia West Administrator. And I know that the thanks for code drill is not the sufficient. I should give much more because they accept my request to host this contest in their platform within 4 weeks of time. I think I contacted Lala only in the month of July only, because I lost my mother in the month July. So, and June I was busy with her, so I cannot start all this proceeding and from June. So this is why I was quite a bit of late, but still Bala has accepted my request, and he actually cooperated, and he managed very well. I will always appreciate his effort. And I extend my heartfelt thanks to whole team of problem setters. And I'm also finding few of them are present here also, judges and the system admins, for the smooth conduction of the contest. I'll appreciate the organization Code Drill for excellent management and cooperation. So my dear contestant, this time has a limited scope for that we have to host our contest in on-site. But we try on-site contest is we have only done through online contest. But we know that in the upcoming regional contest for 2021 will be hosted in between November to January, anytime between November to January, November 2021 to January 2022. So only 3 or 3.5 months will again engage in the regional contest. And this time, since we have a time limits and everything are there, the time limitations are there, so we host only one round regional contest. But this is the first time also the one round regional contest. But in future, in the next ICPC, we are looking for again this is 2 round contest, first prelims and then the on-site contest. If everything is okay, then we'll go for the on-site only. And on-site, the excitement is more because this is Gwalior is hosting for the last 6 consecutive time, and we have observed that on-site contest has given more excitement to the this contestant also, and we can also observe and we can also feel more excited to host on-site. And this next coming regional contest, we are looking for more team to participate. So, and we are also unveiling that this ICPC Gwalior will host multi-city on-site regional contest. We are hoping that if everything is fine, then at least 6 to 7 geographical location will host the ICPC regional on-site contest. And we are also targeting that on-site contest will be a huge excitement for all the teams. So I'm looking for a good number of teams can participate in on-site, and I hope that this will be double the number that last time we host the on-site contest. So and since this time we are everything we had done very short notice, but still Code Drill has managed excellently, and I must thank the Code Drill for this effort and the cooperation. And I also think that in future also I can take help from them for this contest. And a special thanks to all the contestants. I think this time was minimal mail I received. Still, we have a threefold more on-site this regional contestant teams, but they have also cooperated a lot. And you know, in this contest, your team has unable to solve many problems, and I know that you have tried hard during the 4-hour contest. And this is 12 problem in 4 hours. It is also, I know that time tight, and we got very competitive team performance also. And since you have unable to solve 4 to 5 problems, at least you have unable to solve 4 to 5 problems, means if we see the top team has solved only 7 problems, so it means that at least 5 problems you are unable to solve. But today we are hosting a problem discussion session which can help you to know that the problem, how to solve that particular problem you have unable to solve during this time tight situation. And I can hand over this to Bala, because he can coordinate with all the problem setters present here, like Udit, Ashim, Kevin, and all. So I know that few will be, few are not here, but still I know that a good number of problem setters are present here. So, and a few more queries that you have asked, that what are the goodies and when the rank will be published. And as now I discussed with the drill and the team, they said that within a day they can complete all this check, and then most probably by day after tomorrow, the final list I'll publish in ICPC global site as well as our local page also. And about the goodies, I will also announce that after getting the final rank list, I will also decide that how many teams will get goodies like T-shirts and cash award, and everything will decide after getting the final list. So I can over to Mr. Balaji from Code Drill. So now you can say something and start the problem discussion session. Okay, thank you. Thank you all.
Thank you, sir. Yeah, so like for Gwalior, when sir contacted me, I was not sure like how we would do that, but really awesome work from the setting team who all stepped up and ensured that within a short time all the problems were completed and tested and everything. So yeah, I mean, I want to thank them. They have a really awesome team. And yeah, without much further thing, let's move on to the problem discussion itself. Vichitra will be hosting that. Vichitra, over to you.
Yeah, sure. Hi everyone, welcome to the session. We will start with the discussion now. So before that, I would go to the credits section. So thanks Balaji for judging the whole contest. Then I was the admin for the contest, and then we had few coordinators, Ashish Gupta, Kevin, Vaibhav, and even Jatin helped us. Then problems were mostly set by Kevin, one problem by Jatin, one problem mine, and yeah, one problem by Sarang and Vaibhav. Then whole the testers team, Kshitij, Kevin, Jatin, Ashish, Ajinkya, Udit, Divyansh, Naveen, Saswat, Samaditya, Sunit, Ritul, Varad, Aswin, Sarang, Vaibhav, Hitsa, and Mank. And Deepa for platform coordination, and RCD, Dr. Jyotip Dhar for giving us the chance to host the regional round. So yeah, so in the regional round, we had 12 problems equally distributed over the set. We thought yeah, it would go like we estimated, but yeah, unfortunately, that wasn't the case. Uh, the estimates by us, like it's quite off, but yeah, overall the set still looked good to be called balanced. So first problem is the Jeff, that is cakewalk problem of the set, and 509 teams solved it. It was authored by Kevin, and image credits Sarah, and I would be taking up the explanation for this problem. So in the problem statement, basically we were given a train, and then basically there was a person who was running through the train from the back to the front, and then there is uh, so basically then there is Jeff who is trying to like eat the whole train one by one. So in one step we can move to next block, or if there is some blockage in the one of the chamber, then we can clean it. So only these two types of operations we were given. So this is the like very easy problem. We can just check uh, like if next set of the chamber is free, then we just move to next one. If it's not free, then we just clean it, and next move we again move to the next chamber. So that way like we can just simulate this process, and if we are able to reach the front, then Jay wins. Otherwise Jeff is able to eat the train and Jeff wins. So that was the solution, and I think pretty much easy constraints, and also we can solve it in uh, given time limit and with the given constraints. Then the second problem, the cat one. So 556 teams solved it, and Vaibhav authored the problem. So like this was, I think, included in the set at the very end of the a time when we thought that yeah, set is quite more on the difficult side. So we included this problem to maybe add some easy problems so that even the lower ranked teams are able to solve something. So in this problem, basically, we are given some cats and as of each cat, and so for like we want to find a subsequence such that the ith cat is there in the subsequence, and the size of the subsequence is odd, and then like ith cat as is the median of the given chosen subsequence. So that was the yeah. So just a second. So yeah, that was the statement. Like for every I, we wanted to find out if this particular cat is the median of the given array, then what is the largest size of the subsequence we can take. So the greedy insight was that we can sort the array. So after sorting, like we would obviously manage like what was the initial position of the cat. Then like we can pick all the elements which are in the left or in the right, and then we consider that if in the left there are x elements, in the right there are y elements, then we pick the minimum of them. So that's the logic. So if you can say that yeah, if there are if the ith cat, like after sorting we are considering the ith cat, then I minus one elements in the left and n minus I elements in the right. So we take minimum of them and multiply by 2 to include both the left and right, and the ith cat is also included, so plus 1 for ith cat. So that was the logic, but then the only thing we needed was to consider the duplicate values. So to consider duplicate values, again, like we can just consider the unique values, find the answer for them, and then we can just iterate over the initial set of the cats and just answer each query. So we can easily do it by maintaining set or map by n log n. So then we had Apple problem, which was authored by Sarang, and 368 teams solved it. Yeah, this is another problem which again we included. Like initially we had two more problems with the difficulty around medium hard. So like we thought that the current set is like quite hard, so we thought of removing those two problems and putting easier problems. But yeah, given the time, we could not come up with more easier problems. So this was again thanks to Sarang, who came up with this easy problem, so that like it became much more balanced set. And in this problem, basically we were given an array, and like we wanted to find out. I will just take up the initial version of the problem. So we wanted to find out max of any subarray minus min of any subarray, and we wanted to minimize the difference. That was the initial statement. We can take any subarray, but then we introduced the number of queries in it. So like after each query, we can update a particular element, and then again we want to answer the same question we were given initially. So the main observation was that it's always good to take just two side subarray, because consider any subarray, and like if we want to add one or more element in the subarray, then maximum would always increase and minimum would always decrease. Like it's not like it will it can either stay same, but it can't increase. Like minimum can't increase, because let's say in the set there were 3 4, we add 2, then minimum becomes 2. It's not other way that minimum can go up. So it was always beneficial to just pick two sides subarray. And yeah, proof is just simple, that you can see like take any two elements, try to add it, and then you see that yeah, either maximum increases or minimum decreases. And then because we wanted to minimize the difference between max and min, it's always beneficial to take the just continuous elements. So yeah, that was the main observation needed. Now like for the update, now like consider updating any element a of x. So you see that the only two things which change the difference between x and x minus 1 or x and x plus 1. So we just need to update these two things. So we can update maintain any data structure which can do like this kind of update. So I think easily we can take a multi-set or priority queue, something like that, and we can just use log n operations to insert or erase the elements, and then yeah, that should be enough to solve this problem. And like every query then takes log n time and total n plus q log n time. Then fourth problem was Dimitri's queue. 141 teams solved it. Kevin was the author for this problem. And yeah, this was one of the ad hoc problem. Not much knowledge, any knowledge needed for this problem to solve. Just find out like this is the structure and some cases, and you should be able to solve this problem. And Udit would be taking up to explain the problem.
Okay, next.
Yeah.
So the first thing we can notice is that we can fill any row with using 1 cross 2 and 1 cross 3 dominoes. So if it's an even number, we can use 1 cross 2 repeatedly, and if it's an odd number, we can use 1 cross 3 and then repeatedly use a 1 cross 2. Next. So if ij is not the second cell from any sides, so I is greater than 2 and j is greater than 2, I is less than n minus 2, all those conditions, then we can individually fill all sides surrounding it. I mean, both the left and the right sides, as well as we can fill rest of the rows like we just saw. So, and we can do similarly for columns, just fill above and below and repeat for columns. Next. So now the only case needed to be considered is that when the cell is at 2 cross 2 from either of the corners. So it's either 2 cross 2 comma 2, or it's 2 comma n minus 2 comma n minus 2, or something along those lines. So what we can do is, if C is greater than 3, the first case is C is greater than 3, so we can fill the first column, and then it becomes something of the form of 1 comma 2, so we can use the previous solution. Next. And we can do similarly for column case, and there is one case left, which is R is 3 and C is 3, and you can see the construction given here. So we use 1 by 2 dominoes in a spiral. Next. So after this, we can the first implementation tip would be to not handle every case distinctly. For example, when you have 2 comma 2 and n minus 2 comma n minus 2, so you can handle them together, so that will reduce some casework. And for doing the numbering, the letter numbering, so you can either pre-assign some values such that there are no some intersections of the wrong form, or you can just greedily assign them, just do a DFS from any position. That would also work.
Thanks, Udit. Then next problem we have by and large, which was again supposed to be an EG. And again, this was authored by Kevin. 229 teams were able to solve it. And Udit would be taking to explain.
So the first observation is that 2 items can eventually become related if and only if they belong to the same component. So this is one condition. This is the minimum condition required for them to become related eventually. Now, suppose so we can. This basically gives us that we can solve each component separately. So let's see what will happen if we're only working for one component. So what we ideally want to do is that pair the smallest one with the biggest one, and so on. But we need to check if that's possible to do. So let's assume that costs are C1, C1, C2 till Ck. Now in the optimal solution, we will have the lower half as we'll use that 2 times. The middle part, as in if it's odd, then the middle part we'll use it 1 time, and the remaining part 0 times. So we have categorized this into low, high, and middle. So first of all, let's assume that the total number of things in the component is even, because if it's odd, then we can just remove the middle element and the component will remain connected. So we now have a left half and a right half in the component. So you can observe that there will exist at least one edge from the left half to the right half because the graph is connected. So we can, instead of pairing the minimum to the maximum, we can just pair any item from the lower half to the higher half, and it will still hold the property that the sum remains the same. And you can also observe that removing those 2 items, the graph still remains connected. So this is the solution.
Thanks, Udit. Then next problem we have for mode, which was again supposed to be something like easy medium. But we got only 16 submissions to this problem, and then 16 teams were able to solve it. Again, Kevin is the author of the problem, and Udit would be explaining it.
So there are lots of solutions possible to this problem, and I'll describe one that's an interesting one. So we can handle many different cases individually. For example, if m is of the form x square, we can just put x, 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 and 3 because x cube is just 0, I mean divisible by x square. And we can generalize this slightly to not just x square, but of the form, but any non-square free number. So if it's p square k, then we can write pk, 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 and 3 because pk to the power 3 will be divisible by p square k. So that just gives 0 plus 0 equals 0. Next. Now, first, so now we know the number is not number is square free, so we can write it as prime times some number k. So let's first consider what happens if just k is equal 1. That means the number is prime. So the first thing to notice is that x to the power m will be equal to x mod m because Fermat's Little theorem. So we are essentially trying to use Fermat's Little theorem to solve Fermat's last theorem. So using x to the power m equals x mod m, we'll get x plus x to the power m plus y to the power m equals x plus y to the power m. So this would be a solution, but you have the condition that the power must be less than m. So we'll have to think of something more. So then we try, instead of m, we can try m minus 1, or so m minus 1 has an interesting thing that x to the power m minus 1 is always 1. So we can try x, so some number, if n is m minus 1, then the values will be 1, 1, and 1, but 1 plus 1 is 2. So this also doesn't work. We'll have to think of something else. So now we can try m minus 2, and now we have x to the power m minus 2 is 1 by x, which is the modular inverse. So we can observe that 1 by 2 plus 1 by 2 is 1. So we can choose n is equal to m minus 2 and put 2, 2, 1. So because that will give you 1 by 2, 1 by 2, and 1. So they add up. And instead of this, any fractional equation will do. So 1 by 6 plus 1 by 3 is 1 by 2, and anything like that. So now we also need to ensure that x, y, and z are greater than 2 and less than m. So I will show how to fix that later, but let me just complete the non-square free case. So we can write it as m equals prime times the number k, and then whatever solution we get for the prime p, we can just multiply it by k, and it will be valid for m is equal to pk. We could also use, in the instead of Fermat's last theorem, we could use Euler's theorem. So in that, in Fermat's last theorem, we had x to the power m minus 1 equals 1 modulo m. Instead of this, we can use x to the power phi m minus 1 equals 1 mod m, and we can get something similar. So the only thing left to do now is to fix x, y, z to be greater than 2. So you can, the most easiest way to do is you can multiply it by some number, all the values x, y, z, so by some number. It doesn't affect the modular equations, just changes the range of x, y, z. So we can multiply them with sub numbers such that they are between 3 to n minus 1. The most easiest no-brainer thing to do is just randomly keep multiplying them by some natural numbers till the equation fits. So that's what I did, and that will work. But you can, but you'll also need to handle some small cases separately. So like 4, 5, 6. So it turns out only the case m is equal to is impossible, and rest you can handle.
Thanks, Udit. Next problem we have Senobu 7, like which was a geometry problem. So yeah, we we kept this problem, although like testers suggest us to not have this problem because the set was much more difficult now. But yeah, because generally Indian engineers don't have geometry problems, so we thought of keeping one geometry problem because world finance generally have one geometry problem. So that was the main intention. Kevin was the author for this problem, and one team was able to solve it. And yeah, there is a story behind this problem. Like at the end, there were two more teams who were very close, but they could not solve it. But then, like because of them, we had to verify the checkers that yeah, they are indeed correct, and we did not miss anything. Because one team had a very stupid mistake, like instead of else they put else if, and then there was one more team who were not able to put the polygon coordinates in the right order. So yeah, like quite sad for them, but that's what it is. And Kevin would be explaining the problem.
Okay, thank you. So I'll be explaining this problem. So the first thing you notice here is that you're given the areas of 7 regions that are formed as a union of some subsets of the polygons. The problem here is that that's a bit hard to think of because there are some overlaps between the regions, and so it may be hard to think of how to construct the polygons that you need. So the insight here is that you can convert it into something else. For example, if you have 3 regions, then generally you have it separates the plane into 8 regions. One of them is the outside, and that's infinite, but the remaining 7 will be finite. Next, please. So yeah, so as I said, it's much easier to think of the 7 disjoint regions instead of the overlapping regions. And thankfully, there's a way to convert the given areas into the areas of the 7 overlapping regions. And so for the following, here's a bunch of notation we will use. So a boldface means the area, otherwise it will be the region. Okay, next please. So here's what I mean. So the given 7 regions in the input are on the right side, and the disjoint regions are on the left. And there's a way to convert the sizes of the areas or the areas from one to the other. So, and it's a very simple system, and you can do it by hand. And okay, so this is the exact system, and this is perfectly invertible. And now using this, we can solve for the areas of the disjoint regions. Now, if any of those disjoint regions has a negative area, then it's clearly impossible because there are no overlaps anymore. So that's the first condition we will check. All numbers there must be non-negative, but it turns out that if all of those are non-negative, then there is a solution. So for example, the most general case, I guess, is if all the disjoint regions have a positive area, then there's a simple construction, and it involves placing the intersection of everything first and calling it the core or something, and everything else will be offshoots or will be attached to that core. Okay, so another thing we want to think about here is that the areas are integers. So you can also think in terms of a grid. There are solutions, there are multiple solutions to this problem. Some of them actually create grids. And this one, I will just describe an ad hoc solution. So here, all 7 regions are positive, and here's one general way to construct the solution. So the core here is in light blue, and everything else branches off from that. And as you can see from this diagram, each region, say A, forms a connected component. You have to ensure that because we are only allowed to create polygons. We are not allowed to create disjoint regions for A, B, and C. But in this construction, you can notice that A is connected, B is connected, and C is connected. So that's the main challenge here. You have 7 disjoint regions, but some of them have to be connected. and you have to figure out a way to connect them while maintaining the area or having a very specific area. So next, please. Okay, so the construction previously assumed that all 7 regions have a positive area, but it turns out it works a bit more generally. Even if some of the regions are 0, it still works. The only important thing is that ABC must be positive. The core must be positive because everything connects to it. But everything else can be 0, even all of them. So the remaining cases must be when the core is 0. So one of the easier cases is if one of those 2 overlapping regions is 0. Because in that case, you can just put everything into a line as illustrated here. So some of the regions again here may be 0, but this solution will still work. So this handles a lot of cases. And what remains is when the only remaining case now is when the core is 0 and all of those 3 overlapping regions are positive. Okay. So there's a question, and the question is whether there's a way, whether it can be shown that the areas of the overlapping regions are integral or are integers, and the answer is yes. And just look at the formula; they all involve just additions and subtractions, so they will definitely be integers. That's the main reason. Anyway, this is the last case, and as I said, the core is 0, but all 3 overlapping regions are 0, or non-zero, I mean. So there are multiple ways to handle this case. This is the way I handled it, and the way I handled it, it's not a pure grid anymore. If you look at the shape at the bottom, there's a diagonal, 45-degree diagonal there. The reason for that is that we have to connect all those 3 pieces together. And if one of the pieces is too small, then we have to do something like this. But other than that, it's mostly the same. And the area of those diagonals are easy to handle anyway, because that's just half of a square anyway. So yeah, this is the last case, and I think with this, we have already handled all cases. So, okay, the implementation, this is just O of 1 because we just handle all cases, and each polygon here has at most 8 vertices or something. There are other solutions. Even slower solutions will pass because the time limit is a bit generous, but that's pretty much it. If you have other ideas for the solutions, then maybe that will work. Then just go for it, implement it, submit it, and then hopefully it will pass. All right, thank you.
Thanks, Kevin. So next problem we have is the Nilo in Wonderland. This problem was again a medium problem, and 7 teams were able to solve it. The problem was authored by me, but yeah, there is some story about this problem. Like, we thought that most of the teams would try FFT in this problem, and that was true, that most of the teams were trying FFT, but they were not able to solve it with FFT. So like the TL was kind of like that FFT won't pass. It was taking much more time, and then there was a clever DP solution, so that would work very easily. And yeah, I authored the problem, and Kevin would be explaining it. Over to you, Kevin.
All right. So yeah, as he said, there are several FFT approaches to this problem, but in fact, there's a much simpler solution that just involves dynamic programming, and that's what I'll be describing here. So the first thing we notice is that there are 4 types of movements. It depends on whether there's a question mark on either the die result or the direction, left or right. So we just enumerate those 4 types here, and at the bottom, the corresponding possible offsets are enumerated. And I think that's fairly intuitive, but we just need to note those. All right. So the first thing you notice is that some of the offsets can be negative because, of course, if we move to the left, the offset will be negative. There's a way to make those non-negative just for our convenience. It's not necessary. Some solutions will not need to do this, but for the solution I'll be describing, let's just make everything non-negative. So the idea is to find the leftmost possible position, and that corresponds to taking the leftmost possible offset for each of those 4 types. And let's call that leftmost position P. And now, using P, all of our offsets are now non-negative. And in fact, all of those sets will have 0 in it. Okay, so for example, the second case where V question mark, previously it's either move V to the left or right, but now it means stay or move 2V to the right, because now we're starting from the leftmost position. We're relativizing everything to the leftmost position. All right, so most of our offset sets are now of the form 0x. In other words, a lot of our sets just has 2 elements, but we have 2 sets that don't have 2 elements, specifically the 3rd and 4th types. For example, the 3rd type has 6 elements because it corresponds to the 6 results of the die, but we can convert them into sets of size 2 because the result of a die is equivalent to 5 tosses of the coin or something. So that's the idea. We convert everything into 2 sets. Even the 4th type can be converted. So now we can assume that all of our sets are 0x for some x. Now, using those sets, we know that there are only 12 possible sets because the largest deviation from the leftmost position is 12. And in fact, only 8 of those are possible. So now we want to find all possible locations. So we start, our initial set of locations is just 0. It corresponds to starting at the starting position. Technically it's P, but we can just adjust later. So let's assume it's just 0. And now for each of these 8 types, we will transform our sets of locations into a new set of locations while involving the next type. So here I use the notation S sub x to mean the set of possible endpoints if we only consider the offset types up to x. So initially it's just 0, and we want to eventually find S of 12. And so the algorithm will involve computing S sub x given S sub x minus 1. In other words, we will consider type 0x. Okay, so what does S sub x look like? The expression is simply below. It's a union of a bunch of sets involving S sub x minus 1. This is fairly intuitive because we have if we have C of this type, then we simply allow ourselves to choose any number of them between 0 and C. So each of these sets just corresponds to picking a particular number of this offset type. So another way to phrase it is in the 3rd bullet here, given some S, an element of the previous set, it generates C plus 1 locations, and all of those are spaced X apart. But here we now notice that it's very similar to a range update. So we're now seeing a faster way of implementing it. So it's almost like a range update, except that the offsets are X instead of 1. So, but that's not the problem, especially since we can process everything offline anyway. So here's our algorithm. So given S sub x minus 1 and our offset type, we create an array, and this array will represent the counts of each of those generated positions. So for each element of the previous set, we increment a particular element of A and decrement another particular element. So instead of incrementing C plus 1 times, we will just do this, and then later on we will just run through a loop that will accumulate the array. So this is fairly standard. So I think I will just gloss over this part, but I think it's fairly standard, so it's easy to follow anyway. So if you do this step, notice that it's almost linear in the sides of the array. In fact, the complexity is written below, d squared n, where d is the size of the die. Definitely it can be improved, but it's not necessary, and this is probably the simplest solution you can think of. So yeah, instead of using FFT, we can just use dynamic programming. Okay, so next slide, please. So why then FFT? So why do teams think of FFT for this problem? It's because the counting involved in this problem can also be phrased in terms of polynomials. For example, the offsets can be put as the exponents of some variable x. So remember our offset sets earlier. This is the corresponding polynomials for them. Okay, next please. The nice thing about these polynomials is you can multiply them, and that will correspond to discovering or knowing the possible locations. If you multiply two polynomials here, then the corresponding product will encode all possible locations. Specifically, all the terms with non-zero coefficients will be the possible locations. That's why teams were thinking of FFT here. So even the step we did where we looked for the leftmost offset, that can also be phrased in terms of polynomials. It's just factoring a certain power of x. Yeah. Okay. So yeah.
Thanks, Kevin, for explaining the problem. Now, next problem we have is Lala Langtons, and again authored by Kevin. And this problem I think only one or two teams tried it, but no one was able to solve it. We had 0 solves, but yeah, this was like fairly easier than the harder set of the problems. But still, I think it's just lack of the teams who tried it. But yeah, Balaji would be taking to explain the problem.
Yeah, so next slide. Yeah, in this problem, if we go via normal grid traversal, then it won't go anywhere, obviously, because the main problem here is that the state of the cell, the color of the cell changes with each step. So the only way to do a naive grid traversal would be to keep track of the entire current state, and that obviously won't work. So let's see if we have any insight. The crucial insight is that the path can't cross itself. In other words, a cell can only be visited once. So why is this the case? So let's first see how the path will look like. So suppose we start at a cell with a color. I will just use 0 and 1 for the colors. We start at a cell with 0. Then the next step that the AND takes has also to be 0. And the cell after that has to be 1. And the cell after that has to be 0, and so on. And that's because whenever an AND arrives at a cell, its color changes. Now, the observation here is that if we start at a cell, then all the cells which are at an odd distance from this particular cell will be of the same, will have to be of the same color as that cell before the flip starts. So whenever I say this statement, it's always before the initial state of the grid. And all the even distances path has to be of a different color, the opposite color of the starting cell. Now, the crucial observation here is that if a cell crosses itself, then that means if we start at a particular cell and again reach the same cell, that cell is always at an even distance from itself. This is because if you go right, then you will also have to go left. And if you go up, you will eventually have to go down. So there is always a matching between up, down, and left, right. So the eventual path when the cell again reaches itself is always even. And since it's even, it has to be of a different color. But since it's the same cell, it has the same color at the start. So we can conclude that the each cell has to be visited only once and the paths can't cross. So with this observation, how does it look? If we start from a particular cell and mark all the cells that are reachable, then it will look something like the graph shown here. And here we have to traverse only through the white cells because those are the reachable ones. And how do we do that? Like we observed, it has to be of alternative color, except for the starting cell. So if you start with 0, then the next has to be 0, but the one after that has to be 1, and after that 0, and so on. So we can mark these cells as reachable and non-reachable. So now the problem becomes, next slide please. Now the problem becomes finding a path from A to G to P which does not cross itself, and so it can either be via, so it has to start at A and it can visit G first and P next, or it can visit P first and G next. But like since we don't know what is the optimal path, we can just try both of them. And in all of them, each the cell ant has to go through each cell at most once. So now we can't use simple BFS or DFS since the crucial part here is that each cell has to be visited by one. So if you think of it, it's like a capacity of a node. Like once you visit a cell, you have used up the capacity of that cell, and you can't do that. So that suggests max flow approach. So let's see next slide. So the approach here is that we have to find two disjoint paths, A to G and G to B. But finding that in max flow is a bit difficult because G has both an incoming and an outgoing increment. So we flip the one of the parts and say that let G, the middle visiting cell, be the starting point, while the other two are the endpoints. So we need to find a disjoint path starting from G and ending at A and P. So this can be achieved in a flow network by having G as a source and having A and P as sinks. And remember that this is still node capacity. So each cell has to have capacity 1, and the max flow of this cell has to be 2 if there is a disjoint path from A to G to P. And once we have this path, we just need to invert the path from G to A so that it is from A to G, and then just append the path from G to P ahead of it. So like this is the transformation to a flow graph. And after that, there are some two standard techniques that we need to use to get the actual solution. I won't go into detail, but this can easily be searched. The first technique is to, there are two sinks here, but in flow algo, we require only one sink. So we need to convert a multi-sink to a single sink network. And the second is all the capacities here are cell capacities or node capacities. But we need edge capacity. So we need to transform the node capacity graph into edge capacity. Now it doesn't really require any fancy flow algorithms. A simple 4% would be enough because the max flow is just at most 2. So we'll just require 2 augmentation at most to find the both the paths. Now, if you see the path, we need not worry about the 4 RC limit because we have 2 paths and we know they can't repeat, so it will comfortably fit within 4 RC. Now, the thing about this problem is that if you are only used to building flow networks and directly using the library, you might have some difficulty solving it because you need to go like break down the library itself to build back the path. So you need to keep track of like what are all the parent capacities or the residual network capacities to figure out the actual flow. So you will need some knowledge of how the flow algorithm itself works, or at least how your library template works to figure it
out. Thanks, Balaji, for explaining the problem. The next problem, we have passed the message, which was again kind of medium problem, but no one tried it. Maybe looking at the large numbers in the statement. Kevin was the author of the problem, and I think Kevin would be explaining it.
Okay, so so we are given a tree, and essentially we want to find the sum of the squares of the bitwise XORs of the numbers. Not exactly though, because there's a fixed number in the statement that you also have to XOR to the numbers. But that's a minor thing that can be easily fixed as well. So the first thing we need to check to study here is what is the effect of squaring to a binary number, because XOR is essentially a binary operation, and squaring is more of an arithmetic operation. So yeah, so let's say we write a message in binary like this. What happens to squaring it? It will become a double sum, and then in each sum we will iterate over all bits. Therefore, in the square there will be interaction terms between bits I and j. So the solution will involve computing the contribution of the interactions like this. Okay. Note that for each message, it only depends on the ith bit of the numbers. So the ith bit of the message only depends on the ith bit of the numbers. So keep that in mind. Okay. So let's say the messages are listed above, M1 to MP. So we want to find the sum of their squares. So using some algebra, it turns out that the contribution of the ith and the interaction between the ith and kth bits will be the sum of the contributions of the ith and jth bits of each of the individual message. Okay, so since there are few bits, but there are many messages, we want to be able to find the inner sum here quickly. So in other words, given a pair of bits, we want to find the sum of their contributions very quickly. Okay. So remember that we want to find the interaction between bits I and j. And since bits I and j only depends on the bits I and j of the nodes, then for each node, we naturally keep only 2 bits, their ith and jth bits. In other words, for each node, we only remember 2 of its bits, and so the only remaining values will be 0, 1, 2, and 3. Therefore, the only possible XORs will be 0, 1, 2, and 3, and our goal is to find the number of paths with each of these possible XORs. And that's a bit easy because there are only 4 possible values. We can do something like dynamic programming on the tree, and that will just take linear time. So my only implementation tip here is to pre-compute the traversal of the tree, because we'll be doing this traversal for each pair of bits, and then there will be log squared m bits possible. Okay, so that's the idea. That's the main idea, but naive implementation will probably not pass because mainly because m is large here, and so the constant as well can be large. But there are some optimizations that can be made. For example, I and j contributes the same as j and I, so we only need to do it for one of those pairs. Another one is that the bits beyond log n will be special because the bits of the nodes will be 0. So in fact, we can handle most of them at the same time. So that reduces a lot of the work. Instead of log m, there'll be only log n bits that need to be handled. So finally, as I mentioned earlier, just compute the traversal of the tree once so that we don't have to incur that constant every time. So yeah, that's mainly it. It's just dynamic programming on the tree, and you just need to find the contributions of all pairs of bits. All right.
Thanks, Kevin, for explaining the problem. The next problem, 11th problem we have is house hunting, which was authored by Jatin Yadav, and I think only one team tried it, but no one was able to solve it. And Jatin would be taking to explain.
Okay, so yeah, so in this problem, you're given a tree and you have to find k vertices on this tree such that the maximum distance between any 2 of those vertices is minimized. So naturally, let's consider the endpoints of the diameter, that is the 2 nodes A and B amongst our chosen k nodes that have the maximum distance between them, and say D is the maximum distance, and let C be the midpoint of the path between these 2 nodes. Now this C can either be a node of the tree if this path has an even length, or it can also be a midpoint of an edge if this path has an odd length. And so we know two observations about this node, this C, which is that all the k nodes must be at a distance less than equal to d by 2 from C. For otherwise, if there was some node x that was at a distance greater than d by 2, then if that node x was closer to A, then B and x would have a distance greater than D. And if that node was closer to B, then A and x would have a distance greater than D. So that would be a contradiction. And the converse of this statement is also true, which is that if there is a vertex or an endpoint or an edge midpoint from which all of the k nodes are at a distance less than or equal to d by 2, then any two nodes have a distance less than or equal to d between them. This is because for any two nodes x and y, we can go from x to c and then c to y. And both these individual distances are less than or equal to d by 2. So the total distance will be less than or equal to twice of that, which is less than or equal to t. So yeah. So based on these observations, let's reduce our problem into an equivalent problem, which is, first of all, let's also consider nodes at the midpoints of these edges. So now we are going to add n-1 new nodes in our tree. So let's say the new tree is t prime, and in this new tree there will be 2 n-1 nodes, n original nodes and n-1 new nodes. And now every edge will connect from the midpoint of t to one of its endpoints. And now in the initial tree, if the distance between any two nodes was d, in the new tree prime, the distance now becomes 2d, because every edge you have to go to midpoint and then to the other endpoint. So it gives a cost of 2. Now in this new t prime, let's define f of c comma d to be the number of nodes that are at a distance less than or equal to d from c in this new t prime, and the distance refers to the number of edges in t prime that we have to traverse to go from C to that node. And we have to find the minimum d for which there exists a node from which there are at least k nodes at a distance less than or equal to d. And these nodes, they have to be from the original tree. So k nodes of the original tree that are at a distance less than or equal to d. Okay. So we are going to do some pre-computation before we actually get into the problem. First of all, we are going to need the order n log n pre-computation and order 1 query algorithm for the lowest common ancestor. Here, if you don't know about it, you can Google it. We just form a sparse table over the depths of the Euler-Tor tree and then convert it into a range minimum query. And we also perform centered decomposition, in where we are storing two things. For every node x, we are storing in the subtree of x in the central decomposition tree how many nodes are there which were at a distance less than or equal to d. And similarly, for every child also of x prime of x, we are storing how many nodes are there in the subtree of x prime that were at a distance less than or equal to d from x. So using these two arrays, prefix x and prefix to x prime, we can we are going to use these two arrays to answer the calls to f clearly, easily. So now, okay, so now let me explain why we can store these prefix arrays easily. This is because d has to be less than or equal to the size of subtree, because every subtree of a centroid tree is also a connected subgraph in the original tree. So which means that if the size was x, there were x nodes in the subtree, then any two nodes were at a distance less than or equal to x minus 1. So d has to be also less than or equal to x, less than or equal to the size of subtree of x. So this means that overall, when we sum it over all the nodes, as we know that the sum of subtrees is order n log n in central decomposition, so total time here would be order n log n. Next. Okay. So now let's see how we can compute this, compute a call to the function f fast. So we are given a node C and a distance d, and we need to find how many nodes are there in the original tree that are at a distance less than or equal to t in t prime from C. So we can iterate over the ancestors of C in the central tree. And for example, say there is an ancestor x which is at a distance d from x. Then we need to add the contribution of all the nodes that are in the subtree of x, and then we also need to subtract the contribution of the nodes that are in the subtree of X prime, which was the child of X that contained this node C, right? So using this, we can answer the queries in order log n time, queries to the function f in order log n time. And now one standard approach can be just to binary search on this value d and to find if there exists a node with f of c comma t greater than or equal to k. So every step will now be order n log n time, and there are log n steps. So this is an n log square n algorithm, and this is fast enough to get an accepted vertical. Next. Yeah, so let's try to improve this now. We'll use a 2 pointers like approach. So the basic idea is that if the answer is less than or equal to d, then we are not going to waste any queries for f of c comma distance greater than d. We're only going to start checking from d minus 1, right? So we are going to do a loop like this, while f of c comma d minus 1 greater than or equal to d, greater than or equal to k, then d minus minus. So, and we can see that if we iterate on C and do this in every computation, either we are decreasing d by 1 or we move to the next node. So in any, so we are not wasting more than one call to the function f for any node C, which means that overall the total number of calls to the function function f would be order n, and hence the overall complexity would be order n log n. So yeah, that's it.
Thanks, Jatin. Yeah, and one more thing that Jatin prepared this problem in like last day only. It was like very quick because we needed to balance the set, but kinda it proved that again the other set became too harder. But still, I think this was a fine problem to add in the set. Now, last problem we have is Waka and Molly, which was authored by Kevin, and surprisingly, 2 teams were able to solve it, which we did not expect at all. This was the hardest problem of the set, and Kevin would be taking up to explain.
Okay. So in this problem, we are given a state of cells. Each cell can be visible or hidden, and there are 2 players, and one of the players, the first one, attempts to clear the whole array, and the other person tries to prevent that other player. So the first thing we need to check here is when is it even possible in the first place to clear the whole array? So in other words, forget about the competition first. Let's assume they're cooperating, or in other words, there's just one player and he's just trying to clear the whole array. When is it possible, and how do you do it? So it turns out that it's possible if and only if the number of visible cells is odd. So this one, you can find this by brute force or pattern matching, but you can also find this with a simple argument like below. So the only argument is that if there's a piece that has an even number of visible cells, then there will always be one. So in other words, however you smack that piece, one of the resulting piece will be even, and that's very simple to see. So it's only possible to clear the whole array if the number of visible cells is odd. Okay. So next, please. So now it's clear what each player should do. So to clear the whole array, there must be an odd number of visible cells for each piece. And so the second player knows what to do now to ruin the chances of the first player winning. And that's simply to make a piece with an even number of visible cells. So so when handed the state, how do you make an even piece? That's very simple, especially if there's a piece with more than one visible cells. You just smack one of the cells in the right place. Just make sure that one of the pieces will be even. So in fact, you only need one turn to ruin it for the first player. So that's the main idea. The first player's task is very hard. He has to ensure that there will be no piece that has more than one visible cell, because if so, the second player will easily ruin it for him. So on the other hand, that's also sufficient. If the first player can ensure that each piece has a single visible cell, then it turns out that the second player cannot do anything about it anymore, because that property will be maintained however anyone smacks the pieces. So in other words, if all pieces has exactly one visible cell, then that will always stay true. So now we have figured out what the first player needs to do. He has to ensure that each piece has exactly one visible cell, and he only has F smacks to do it. Okay. So now we move on to the second part, which is counting the number of states where the first player wins. So so remember, we want an odd number of visible cells. So let's say the visible cells are, the locations of them are in the list above, P0 to P2K. So the odd index ones, P1, P3, and P5, cannot be smacked because that will produce a piece with an even number of visible cells. On the other hand, they must also be flipped. Otherwise, there will be a piece with more than one cell by the time the second player gets their turn, and that just means they will be able to win. Therefore, we have a bunch of cells that we need to flip but cannot smack. So how do we flip a cell without smacking it? So a wave of smacks has to come from one of its sides, so either from the left or right, or maybe both. But since we're minimizing the number of steps, we probably only care about a single wave from either side. So of course, we want to minimize the number of smacks, so intuitively it has to come from the closer side. So if one of the sides is much closer than the other, then it's clear which one it will come from. Sometimes they will be pretty close, and maybe we have two possible choices. So the idea is the minimum number of smacks needed to ensure that each piece has a single visible cell is approximately the sum of the distances of the odd index ones from the closest neighbors. Okay. So that's not exactly correct though, because a single cell can generate two waves going on both sides, which means we save one smack for them. So then the count is a bit more complicated because of this. So sometimes we have to choose one of the sides if it means fewer cells will generate waves. Or in other words, we want to maximize the number of cells that will generate two waves. So yeah, so the condition is a little bit more complicated, but it's on the right approximation. And in fact, we almost already have characterized the states that we want. So how do we count them now? Of course, it has to be dynamic programming. So there are multiple ways to do it. Here's how we do it. So in my dynamic programming, there are two states or two functions, count odd and count even. So count odd is the number of states with odd visible cells that takes at most F max to fix. In other words, this is what we want. But to find the recurrence for this function, we need another function, count even. It's almost the same as count odd, except there are an even number of visible cells. And we also assume that a wave of smacks is coming from the left side. So this is what I chose to implement. There are other ways to implement the dynamic programming, but once you define it this way, you'll be able to find a mutual recurrence on count odd and count even. Okay. So after finding those recurrences, you'll notice that each transition costs O of n squared time. And since there are O of n squared or O of n squared states as well, the overall time is O of n to the fourth. And that's too slow because the numbers in the input can be up to 500. But there are some standard techniques to optimize the dynamic programming. For example, if you will notice the transition, you'll notice that there will be a range sum or a prefix sum of one of the states there. So in other words, we just store another function. We just create another function that just represents the prefix sums, and then include that in our dynamic programming. And using that function, the transition just becomes O of n. Therefore, we can pre-compute all of the answers in O of n cubed time. And after that, all queries can be answered in O of 1. Okay. So this is not the only answer. There's another way to pre-compute the answers. Instead of that dynamic programming, it turns out you can set up some kind of machine or finite state automaton that can recognize the valid strings. There will be n cubed states here, and the transition will be O of 1. So it's very related to the dynamic programming, except the idea or the origin of the idea is a little bit different. But the running time is the same, n cubed. Also, there's a solution that uses a closed form formula, although the proof may be a bit tricky, but the resulting solution will be faster. Okay.
Thanks, Kevin, for explaining the problem. And yeah, finally, on the set, like when we were started preparing the Gwalior set, it was more like we did not have so many medium hard problems. So we thought the set might be actually a bit easier than Amrita one. But yeah, like finally, it proved to be much harder than Amrita set, because yeah, there were a lot of easy and easy medium hard problems. So yeah, at the end of the day, I think it was quite good. So now I would hand over to Balaji if he wants to say something.
Thanks, Suchitra, and I hope like everyone learned to how to solve the problems that you could not during the contest. I would highly recommend solving the problems now, and that's the best way to learn, always solving the problems that you couldn't do in the contest. And finally, I would really like to thank Sir for holding the Gwalior regional despite all the hardships, both due to the situation and personal situation. And I'm sure like I speak for all the contestants when I say that we are really glad this regional happened, given that there were at least one other regional got cancelled and there was a lot of uncertainty around this. So yeah, really thanks. And everyone is like happy that these regionals happened. And I'm sure that in future years, like the number of teams would keep increasing. Yeah. Thank you.
Thank you, Balaji. Thank you, Vijay, for nice conduction of this problem session. And I must thank Kevin, Ashin, and others also. I think Kevin has set many problems, and so he was the almost half of the this problem setter himself, and I'm thankful all the problem setter, and which is also your problem is also only how many team has solved your problem? One harder, medium hard problem, which is I think one team, no? Which is?
I think there were some 16 or something.
Okay. So, and another problem has a less, okay. So I'm just in that it is a nice problem thing. I know that 4 hours time and 12 problem, it is very time tight, and since it is a all individuals can participate independently, so we put more number of problems for this contest. But I know that 12 problems, it is not for 4 hours. You cannot a team, it is unable, but it is a nice contest, and I'm thankful all the problem setter, and especially Balaji is not only judging, he was done tremendous job of this cooperation, and I received tremendous cooperation from Balaji. So thank you all. So we'll looking for the next time, because Balaji won, or that last time means in 2019 December we actually got 2,000 registration, 1,978. But this time I initially announced that I will not go more than 700, as I promised you that I will keep it is less than 700, and I stopped immediately when it is around 700 registration was done. But out of 700, only 524 team has completed everything. So I stopped. I told that no, we'll not go for because we know that it is an online contest and it is a time and everything has to be managed. So I hope in next will be in bigger scale, will go for prelim, but on-site will go for multiple sites contest. And it is a geographically will make in such a way that no contestant has to move 500 kilometers from their place. So at least 5 to 6 places will set for the on-site contest. Okay, thank you. Thank you all. Thank you. Thank you, Balaji and your team.
Thank you.
Now you can close this session, or which